So we've looked a lot into real sequences, but now we're going to move on to series. So if we have a real sequence an, this is the notation we're used to, then the series associated with an would be perhaps a1 plus a2 plus a3, and this is an infinite sum, so you add up all the terms in the sequence for your series. You don't have to start at a p, and I don't know if we mentioned this with with real sequences. You can define a sequence from, you could define xn, but n could be greater than or equal to 10, right? You can define sequences like that. We tended to start from 1, but you don't necessarily have to. So that's something to note, because we're going to have some series where the sum starts from some different value. And this series, our notation would be k is equal to 1 up to infinity of ak. Okay, so that's the more concise way of representing this sum here. What we're going to look at today is a convergent series, and this is something some people struggle to get their head around because we're adding up infinitely many terms. So if this sum goes on infinitely, how can we end up getting finite numbers, which we sometimes, not always, get? And to explain this, I'm going to look at walking between 2 points, and this is one of, I believe, Zeno's paradoxes, and it's not a real paradox, but that's what this is the name for it. And it's if you're trying to get from a point A here to a point B. Okay, so you start at the beginning point A, and say you go halfway. Okay, so to get from A to B, we agree you have to go halfway along, and then you have to go halfway between this point and B, and then you have to go halfway between this point and B. Okay, and the point is you can just keep doing this, and these halves get smaller and smaller. And in theory, if you're only ever going, in each step you're only ever going halfway, how do you ever get to B? Because there's always a halfway between the point you've just got to and B. And if you think about this, say this distance is 1 metre, the distance between A and B is 1 metre, this is 1/2, 1/4, 1/8 of the distance, 1/16, 1/32, and so on. Total distance t is equal to the sum from k equals 1 to infinity of 1 over 2 to the k. Okay, you can see this because when k is equal to 1, we get a half, when k is equal to 2, we get a quarter, when k is equal to 3, we get an eighth, so on. So this is 1/2 plus 1/4 plus 1/8 plus 1/32, and this is an infinite sum, alright? But we know that we're going from A to B, so the distance from A to B is 1 metre, so we know this infinite sum is equal to 1. Okay, so hopefully you can see why, just for us to even exist, these infinite sums do need to add up, some of them to finite numbers, and you can see where this comes from. I mean, you've got to think, as we go on and on, we're adding up tiny terms, alright? So we are essentially equal to 1. And the question you probably now got is, well, how do we know when a series does converge and when not? Well, we have a formal definition, but first we have to look at something called the partial sums. So if we take this series starting at 1, we can have sums leading up to it. So a1, we'd have a1 plus a2, a1 plus a2 plus a3, and so on. And each one of these, as we go down, makes a better approximation of this infinite sum here, okay, because we've got more and more terms of the infinite sum. And we would call this would be from k equals 1 to 1 of ak. This would be written from k equals 1 to 2 of ak. This would be k equals 1 to 3 of ak. And if we did this more generally in terms of p's, because we don't always have to start at 1, ab plus ap plus 1, 1 plus ap plus 2, and so on. And again, this would be the sum from k equals p to p of ak. This would be the sum of k equals p to p plus 1 of ak, and this would be the sum from k equals p to p plus 2 of ak. Right, and the point of these is these sums keep getting bigger and bigger and bigger and bigger, and when we're looking at convergence of a sequence, we want these sums, as we add more and more terms, to get closer and closer and closer and closer to a real number, and then we can say it converges to that real number. So first off, sorry, this is something from the last video, I think. First off, we're going to define the partial sums more formally. So for n greater than or equal to p, the partial sums are Sn, so the nth partial sum is equal to n k equals p ak. As you can see, these partial sums form a series, so it's just a sequence. So the sequence Sn is defined by the nth term of this, and bear in mind n's got to be greater than p, as the sum from k equals p up to n of ak. Okay, so we can now consider this sequence, and that's what we do in the definition of convergence of a series. So we can say a series from k equals p up to n of ak converges to, we'll say, s in the real numbers if the sequence of partial sums converges to s as n tends to infinity. So that is if ap plus ap plus 1 plus an, that has to go, if that tends to some real number as our n tends to infinity, then we can say the series converges, and this should be infinity somewhere. And this makes sense because if you look at our partial sums, it's this series, but instead of infinity we have n. So if we make n tend to infinity, we're going to see, and then if that converges to a real limit, then we can say our series converges. And this is a nice definition because we're quite familiar with dealing with sequences, so we can use that. And in the next couple of videos we're going to look at some examples on showing some series converges using this definition, and then we're going to look at some more complicated series where direct use of this definition is perhaps difficult, but there are some series tests, limit tests, which we can use to find the value they converge to or whether they don't converge in a nice way. So yeah, that's what you got to look forward to in the next couple of videos on series. If you do have any questions about this definition or anything mentioned in this video, then please be sure to let me know, because I know it can be a little bit weird at times, this sort of analysis stuff. But yeah, that's it for today. If you did enjoy, please be sure to like and subscribe, and I hope to see you in the next one.